Hello, and welcome to the final long ISP of my ACES career. This ISP was aimed to squeeze the most out of the 18 Mega 328p using assembly, and as you can see, I'm able to stream live data from a laptop without using a single byte of memory. This includes camera and video streaming by capturing the pixels on the laptop screen and downscaling them, where they are sent off via serial communication to the Nano. So I can actually stream other things on my laptop, not just videos. I also added some new devices and features alongside the wall to further show off my assembly work, the impressive capabilities of the AVR microcontrollers when using assembly, and future ideas in driving NeoPixels. I also managed to glue on all the ping pong balls as you saw earlier. Let's begin at the start. After building the wall and programming some effects, I wanted to fully optimize the software as before I was having issues displaying words or patterns without using precious SRAM and read-only flash. I considered using the more powerful MCUs, but decided to see how much I could achieve with the 8-bit 16 MHz Nano. Port manipulation and high-level C had reached its limitation in optimization, so I replaced some code with AVR assembly to deal with the dirty work of transforming data and bit banging it onto the ports where clock cycle precision is required. To help me analyze the waveforms, I bought an extremely useful 8-channel logic analyzer to measure digital signals. It is what made optimization possible, as I could now visualize the subtle changes I made to the code. For example, this is the waveform generated using the C code developed previously. Now compare that with the assembly code and you can see a stark contrast. These both produced the same effect of turning on an LED, but with the logic analyzer, the difference was made clear in terms of efficiency and precision, with assembly winning out. With this, I continued on with assembly, creating functions to output RGB data, along with masking functions for scrolling messages. This is successfully demonstrated here on the smaller 8x16 RGBW matrix, in which I'll explain the workings of later on, as I didn't have much time to in the last video. I decided to use a mix of C for ease of implementation and assembly for prepping and bit banging the data, allowing me to specify text and background color in C, displaying some cool gradient patterns while assembly does all the heavy lifting. Assembly was first done with the Arduino inline assembler, which is complex, not well documented, and not very pleasant to code in. Nevertheless, I continued writing code with it, but eventually discovered .s files and how they can be called from a C file using the extern modifier, which allows for functions in different languages to be called upon. This was used in the serial live streaming sketch to call on an assembly function I designed and coded to gather serial RGBW data from a computer or another MCU while simultaneously sending out the NeoPixel data, allowing for the aforementioned video and camera streaming without using a single byte of memory. It works by setting the serial baud rate to 2 million, the maximum baud rate an Arduino Nano equipped with an FT232R USB to serial converter can handle. Other Arduino development boards like the Uno or Mega can only support up to 115,200 baud rate with their USB to serial converters, and therefore cannot receive data for live streaming fast enough. Taking a look at the logic analyzer, we see the serial data at 2 megabaud. Here's where the Nano directly reads the RX pin on PD0 at set intervals, gathering data for 7 of the 8 bytes. On the 8th byte transmitted, the function simultaneously reads and bit bangs the 8 bits in parallel onto the whole of port B and the 2 highest bits on port A, as PD0 is being used to receive a serial data. And all this stays within the 40 microsecond time frame in which the NeoPixels don't yet latch. A 0 bit is then required after every 8 bytes of data to prevent reading errors through accumulated error shifting in the serial communication. Reading from such high speeds with simultaneous transmission and data reorganization is only possible with assembly, which is why the USART data register is not used to receive the data. Coding this was a huge feat and took a very long time with timing experimentation and painstaking problem solving of getting to read the data properly and trying to output a clean waveform. Here's where I used some debug signals, denoting where the reading was taking place to help get the timing right. Once completed, it was pretty cool and really impressive to see the camera output, knowing that the basic Nano is currently pulling off ultra-fast and timing-sensitive serial reception while simultaneously bit-banging 2 separate ports to drive and adhere to the strict timing of NeoPixels. Here's a peek at the processing sketch and the data array it sends out. Each column represents the pin number it transmits the data to, with the delimiting 0, and the 4 rows are the 4 color bytes transmitted. So, the color data of 8 pixels are represented in this 32-byte block. Other MCUs like the IoT-capable ESP8266 could also act as a more portable serial transmitter to transmit all the color data, but for now, a processing sketch shows the proof of concept. While coding, I also began gluing the ping pong balls on in small everyday increments where I tested each one afterwards. I had learned my lesson of procrastinating previously. But before I started, I had contacted Bitluti about his wall, and he reported that his LEDs were unfortunately starting to die, probably from the glue. He mentioned using 3D printed diffusers, but since I didn't have a 3D printer handy and I'd already bought the ping pong balls, I decided to put tape around the strips to at least physically protect the LEDs from the glue. So far, it seems to have worked, and there have not been any problems. But if any LEDs do need replacement, the tape can be easily peeled off to expose the LED for replacement without having to deal with all the glue that's on top. In between coating and gluing, I also made a new larger case for the mini matrix with a thicker diffuser, serving as a nice complement to the large ping pong LED matrix. Like the larger version, these strips can be customized to any size and the data flow can be routed with jumpers. I've currently got them configured in parallel mode where each row is controlled by port B and the two highest port A pins. In case of any failures, the NeoPixel strips are hot swappable with the base, where it can be popped off and put back without much work. Like the large wall, the camera and video streaming work as well. Real-time drawing is also possible with a simple processing sketch I made. Here's where I also designed some prototype DDB NeoPixel shields to bitbang data to some SK6805-1515 LEDs with assembly on the ATtiny84. Previously, I had been able to control NeoPixels with the full port of the ATtiny84, but not in assembly. These shields feature an 8x8 version controlled with pin 7 of port A, and a 16x8 version controlled in parallel with the entirety of the ATtiny84 port A. Even with the help of a PCB stencil, placing the LEDs was very painful, and next time I'll probably order larger ones and get JLC to do the SMT work. Even so, part of the 8x8 works, but I have not yet developed the assembly code for the ATtiny to control the individual LEDs, which will also have to happen at a later time, probably when I'm no longer in the ACES program, as the grade 12 year is coming to an end. The ACES journey has been a great 3 years of triumph, failure, challenges, and lessons learned. But through all the hard work, hardships, and all-nighters pulled, I now have a portfolio of wonderful projects and have found my passion for engineering, in which I owe it all to the ACES program, the student support, and its creator and facilitator, Mr. Darcy. Thank you, sir, for always being so patient, understanding, and kind. And although the ACES journey ends here, the content on this channel will not, as I will still continue to expand on my past projects and build new ones. So, stay tuned for more videos, and as always, thank you for watching. It has truly been a game-changing 3 years.